All right, so we're going to be going over conservation of mechanical energy today, which will be, except for one very small thing that we've essentially already done, all review of Science 10. Okay, so if you really got those roller coaster questions in Science 10, you're set because there's not going to be anything really different here. Okay, the only thing we're going to look at is how the work energy theorem relates to conservation of energy, and we've really already done that, but I'll just kind of clear it up a little bit or add to it slightly. Okay, so we need to first off understand that energy cannot be created or destroyed. That is the law of conservation of energy. Okay, no form of energy can be created, no form of energy can be destroyed. We will of course be focusing mostly on mechanical energy, as that's the one kind of most important for us. Okay, understand that energy can be converted from one form to another. When that happens, obviously sometimes it looks like you're losing energy because maybe you don't recognize the other form of energy that it's being converted into. The most common situation for that would be anytime the force of friction is essentially present. Okay? Anytime friction is present, work is done against it, and then the forms of energy produced are usually heat, sound, sometimes light, okay, things like that, that look like energy is being lost, but it's just going into the surroundings in other forms. All right, and then use this concept to calculate other variables related to the mechanical energy of an object. Okay. All right, so there's two kinds of energy, kinetic and potential. We've been talking about those quite a bit here over the last few weeks with work energy theorem. Okay, if we add them together, that gets us our total mechanical energy, which we've also done in the past couple of weeks with work energy theorem. Okay, it means that it also means that if there are any non-conservative forces, like friction is the most common one, okay, it may appear that an object or system loses energy. Okay, that energy is all still there, okay, but it's just been turned into other forms. So essentially what we have here is the work done against non-conservative forces, okay, right here, is final mechanical minus initial mechanical, which is really just the work energy theorem. The change in mechanical energy equals work. All right, so if we ever have a situation where the energy at the end of a situation is different than the energy at the beginning, then we're dealing with a work energy theorem question, okay? Not a law of conservation of energy question. In a law of conservation of energy question, EI and EF are always equal. Okay? And that's the way most of your roller coaster questions from last year started. EI equals EF. Okay? Our initial mechanical equals our final mechanical. If that is not the case, then this applies. And it is essentially no longer a conservation of energy question. Okay? All right, if we're dealing with kind of those roller coaster questions from last year, in our initial position, we would have, and a classic roller coaster that is, you're towed to the top of the first hill. Okay? The towing process is where all the work is done. That's where the energy, mechanical energy, is being put into the system. So you get to the top of the highest hill and you're moving slowly, so you have a little bit of kinetic energy, but mostly you're very high off the ground, resulting in a lot of potential. Okay, so right there. When we go down the hill, that potential energy, turns into kinetic energy. So when we get to the bottom, we have a minimum amount of potential, maybe it's even zero, okay, and a maximum amount of kinetic energy. Okay, then over here, okay, if there's like other little bumps and hills and stuff along the way, because a roller coaster is usually more than just we went down the hill and that was the end of the ride, because that'd be kind of boring. Okay, there's usually loops and other things. Okay, we have that kinetic energy and potential energy always being converted. Now, in a real world situation, obviously there is friction and there's energy lost. Okay, anyone ever stood next to a roller coaster? Okay, is it loud? Okay. Like it's hard to concentrate on that when you're on it because you're busy screaming your guts out. But okay, when you're standing next to it, a roller coaster is very loud. Okay, and sound is a form of energy being lost. Okay, it represents energy being lost. So when we're in Edmonton, when we're at West Edmonton Mall and we're beside the Mindbender, it's actually almost like uncomfortable to stand next to it when it's running. Okay, and the people screaming is not the reason for that. Like that's actually the quietest part of the ride. Okay, but the thing going through the tracks and through the loops is very, very loud. All right, so if we're looking at a typical roller coaster, you have your towing phase, okay, where work is done. Okay, and then you have your kind of gliding phase where it goes down. Okay, and then it might have like another hill or something like that, and then it might have loops. okay, and then kind of an ending point, right? The thing of it is, though, is that none of the other points on the ride can be as high as the first hill, right? In fact, they're all going to be significantly lower than the first hill because this isn't the perfect physical world. If I was to make another hill that was as tall as this one, like right after it, what would happen to the roller coaster? Yeah, I mean, it might be exciting, like, you know, whoa, oh no, and then you go backwards. That might be cool. Okay, if you've ever ridden Montezuma's Revenge at Knott's Berry Farm, okay, that it's actually a ride that does that. The shape of the roller coaster is you start down here and then you get shot through this loop and up, and the ride just ends. Okay, and then you go back down through the loop and you go up this side, and you do that a couple of times and then the ride's over. Okay, but this ride would kind of suck because you get towed to the top and then eventually you just kind of come to a stop here. You probably get pretty seasick from that oscillation back and forth while you lost all the energy. Okay, and then they'd have to pull you all off at the bottom. Can we kind of follow there? All right, so we can't ever have any hill or loop or anything like that as high as the first one because you'd be going very slow when you went through it, or you wouldn't get through it. Okay, so if you want these loops to be exciting, like they are on the Mindbender, okay, they're much lower than the first hill. Okay, that way you're going very fast through them. In fact, fast enough that people often black out, okay, when they're going through the loops. Okay, the Mindbender pulls the highest G's of any traditional roller coaster in the world. Okay, and that's because it's indoor and it's tight. Okay, most other roller coasters, space isn't an issue. They build them big. Okay, they're quite a bit wider and not as tight, but the loops on the Mindbender are very tight. Okay, so as a result, there's a high G-force inside of them. Okay, everyone know what I mean by G-force? We'll talk a little bit more about that in the circles unit, but okay, that's kind of where we're headed. All right. So in other words, the final mechanical energy for a true conservation of energy problem is equal to the initial. Okay, final and initial have to be equal. So consequently, the total mechanical energy remains the same. None of it is lost to friction or other forces or anything like that. Okay, so that's the principle of the law of conservation of mechanical energy. And when we state that mathematically, okay, we write it like this. All right. The next step after that is to expand that out. Okay, so we have EI equals EF, okay, these being initial mechanical and final mechanical. Okay, we know that mechanical energy is the sum of kinetic and potential. So our first expansion is to identify the types of energy involved. Okay, the next expansion would be to put the formulas in. Whoop, that should be enough. Okay, so all three of those mathematical statements say exactly the same thing. Okay, they get more detailed as we move down. Okay, does that look familiar? That setup from Science 10? Okay, hopefully it does. It should. Okay. All right. Now, I'm a geek, and I'm okay with that. Okay? You have to be comfortable in your own skin. I'm a total geek. Okay. I'm also the track coach here. And this little device is at the track field at the U of A in Edmonton. It's where they host provincials sometimes. Okay? And this was one year where we went to provincials, and I saw this thing. And then my inner geek decided to express himself. And I went over and grabbed the whole track team and brought them over. And I'm like, guys, you got to see this thing. And they're like, Coder, it's a ramp. I know, but watch. And when you would put the shot put at the very top of the ramp and let it roll down, they had calculated how much friction there was along this length of track. So the amount of friction that was present in this track would rob the shot put of all the energy given to it when it was up here, and it would roll slowly to a stop by the end of the track. That means, unlike the bowling alley, no broken fingers. Okay, you ever been to the bowling alley? Like you reach down to get the ball, and all of a sudden another one rolls in and smashes your fingers in between. Okay, this one not so much. Okay, as the shot put rolled along this perfectly flat track, okay, the friction stole its mechanical energy and it just rolled to a stop right at the end of the track. It was incredibly cool. I know you're looking at me and going, holy crap, that guy's beyond a geek, but yes, I am, and that's okay. Okay, but it's a great example of law of conservation of energy combined with work energy theorem. Okay, they knew how long this track would be and how much energy would be lost along it. They just made sure they built the ramp high enough, okay, so that any shot put placed on there would have enough energy to roll to a stop at the end of the track. So there's application for what we're doing. Okay? Now, most track coaches that would do, they wouldn't even notice that, but because I'm also a physics guy, it's very cool. Is there what? No, there's no wall. No, it just like it's the end of the track and just kind of gets there. Once in a while, if somebody like pushes it, it'll like fall off the end. Okay, but most of the time it just rolls to a stop right at the end. Okay? It's very cool. Okay? Good application of the stuff that we learn here. All right, now there's a lot of design and stuff that goes into, you have to take this into account when you're designing certain things, certain structures, okay? And this was readily apparent in 2010 at the Vancouver Olympics. Okay, I don't know if you guys remember this, but okay, in 2010 at the Winter Olympics, in the training sessions, there was a skeleton athlete who was killed on the first day because they had not correctly designed the corner wall on one of the skeleton tracks. Okay, and he had too much energy coming into the corner and went up and over the wall. Okay, like normally on a bobsled and luge and skeleton, they go up the wall a little bit and then they come back down, okay, as part of it. But he was going so fast when he got there that he went right over the wall. Okay, went out and he was killed. Okay, so what they had to do for that track as a redesign was they actually started everybody lower. Okay, they moved the whole starting line lower down the track because what did they just take away? A bunch of energy, right? If they start lower on the track, the people, when they get to that corner, will have less energy. As a result, they won't be going as fast on that corner and no one will be able to fly out of the corner. Okay? So it was a solution to that. I mean, obviously it was a design flaw initially, but it was a correction or a solution to that problem. Right? So in bobsled, luge, and all of that, okay, they're great examples of law of conservation of energy because they're on a very low friction surface, right? The icy track, okay, it doesn't have a lot of friction, so they can go very, very quickly. Okay, so if it was a perfect system, okay, at the beginning of the thing, if they weren't pushing, if they just kind of got in the sled, they'd have no kinetic energy and let's say 600,000 joules of potential, so they would have 600,000 joules of mechanical. As they go further down the track to this point, they would have 200,000 joules of kinetic, 400,000 joules of potential, still the same number. So you notice all the way down the track, the amount of mechanical energy remains the same. All that happens is that potential slowly gets turned into kinetic as they go down the track. Okay, so by the time they get to the bottom, all 600,000 joules of mechanical are now in kinetic. All right, questions there? Okay, so I think I have a video of this. I'm just going to double check here. But this is a stunt that was done by Evel Knievel. Okay, he jumped over the Grand Canyon on a motorcycle. Now, it was a narrow part of the Grand Canyon, but that doesn't, kind of cheapen the stunt at all. Okay, he jumped over a giant canyon on a motorcycle, a dirt bike. Okay, and I'm not trying to take away from the guy that walked across the Grand Canyon on that tightrope. Anybody watch that? It's a couple of years ago now. Like I only watched it on PVR, and I already knew the guy had gotten across, and I was like sweating watching. It was freaky. Okay, it got windy, and the guy's got this pole, and he's walking across the tightrope. Anyway, never heard a guy pray so hard in my entire life. He was like praying all the way across. I'm like, you know what? If you got to pray that much, maybe you shouldn't do it. Anyway, so Evel Knievel does this jump where he jumps across the Grand Canyon. Now, the difference in height is not as much, like they're almost essentially the same height on both sides of the canyon. Okay, but if you had this situation where you had a lower height on the other side, that actually works in your favor, right? You get to fly further before you hit the ground on the other side, right? You certainly wouldn't do the trick this way, right? With the cliff being that on the other side, because then you go. It doesn't work so well. Okay, so he actually had a ramp that he jumped off of and he landed on the other side. So let's see if I can find that here. All right, so what we want to do here, guys, is see if we can remember how these conservation of energy problems work. Okay, I want you to see if you can calculate how fast that bike is going when it hits the other side of the canyon. Okay, so he's jumping from a height of 70, moving at 38 meters per second. The ground on the other side of the canyon is 35 meters. Okay, figure out how fast he's going. I'll give you a few minutes on that one. All right, so let's have a look at how we solve this one. Okay, so obviously it's a law of conservation of energy question. So the initial energy and the final mechanical energy are the same. Okay, it doesn't mention anywhere in there about energy being lost to anything. So we're ignoring friction completely. Okay, so we have our initial mechanical and our final mechanical. Since he is 70 meters off the ground and moving at 38 meters per second, he does have both potential and kinetic initially. Okay? At the end, he's still 35 meters above the bottom of the canyon, so he still has potential energy, and he's obviously moving even faster than he was at the beginning, so he has kinetic energy at the end as well. Now we want to expand this out. So m times g times h initial plus 1/2 mv initial squared equals m times g times h final plus 1/2 mvf squared. All right, so we are looking for vf. So is there anything I don't have? Yeah, I don't have mass. Okay, and Zach brought that up. He said, Mr. Coe, don't I need mass? And then he remembered that what I told him last year in Science 10, which is, no, you don't. Okay, in a question on a test, I would give you the mass, but you don't actually need it. Okay, because one time I did this on a test to some people. I didn't put the mass on, and the person came up and we had gone over in class like 100 times why you don't need mass, and this person came up and goes, Mr. Coder, you didn't give me the mass for this question. I was like, oh, it was a roller coaster. I was like, it's 100 kilograms. Kind of looks at me like that was a strange number, goes and sits down. And then another person came up a couple minutes later, Mr. Coder, you didn't give me the mass for this question. I was like, it's 1,000 kilograms. And there's a couple people chuckling because they realize what I'm doing. And then there's a couple of people who obviously hadn't paid attention who are like, oh crap. He just gave them both different numbers. Which one is it? And they didn't really, it doesn't matter. Mass cancels. Mass is in every single term. Okay, I could put in whatever number I wanted because I'm multiplying all the numbers by that same number. Okay, so it doesn't really matter what mass is. I can eliminate it from this question because it's common to all of the terms. Okay, so essentially now I have this. Now I want to get VF by itself, so I'm going to subtract this over to this side, okay, as the first part of isolating VF. So I'm going to have, okay, GHI plus 1/2 VI squared minus GHF equals 1/2 times VF squared, right? I want to get VF by itself, so I'm going to divide the half over. Careful on this one, that half does not cancel, okay, because it has to be everywhere for that to happen. Sorry, there can't be addition and subtraction or it won't work. Now I've got VF there by itself, so I want VF, not VF squared, so I'm going to square root both sides, and I'll be left with this formula here. Now I can plug in my numbers. 9.81 times 70 meters, that was our initial height, plus 1/2 times, he was moving at 38, right? 38 squared, minus 9.81 times 35 meters, the final height, divided by 1/2. Okay, that should give us our VF. Now, you do have to be careful when you're entering something this long into the calculator. You don't want to make any mistakes. So what I typically do is I don't try to type it all in one step. I do it one piece at a time. So I just go 9.81 times 70 meters. Okay, and then I add that to 1/2 times 38 squared. And then I subtract from that 9.81 times 35. And then I divide that by 1/2. And then I square root that. I just find that if I make a mistake, I find it better than if I've got a whole long typing thing to look at. All right, so on the other side, let me move in at 46.2 meters per second. All right, so basically any situation where you're told like something is falling or on a track, but you're told friction doesn't make any difference, okay, you're dealing with a law of conservation of energy question. Okay, a skydiver jumping out of a plane would be a law of conservation of energy question. You could, except the question may ask you solve as a law of conservation of energy problem. Yeah. Okay. What's that? No, you wouldn't need the mass for that one either. But if I was to throw in something about needing the energy for a part B, that wouldn't give it to you, right? So usually that's what I would do. I would say, here's your whole law of conservation of energy question. And at the end, I'd say, oh, and by the way, I want you to calculate this thing to do with work energy theorem. And then you would have to go back and do some more calculating, right? All right. So questions on that? That sort of makes sense? Okay, and like I say, in a question on a test, I would just give you the mass. Okay, you could plug in mass, not cancel it, put it in every m, and you'll get exactly the same answer. Okay, it won't make any difference there. All right, so this is what we just did. Okay, so we've done all of that calculating. Okay, so we're good on that. Okay, I want you guys to try this one. It's fairly straightforward, but this one involves you calculating some of the energies. If you're calculating the energies, like actually getting something in joules, can you cancel mass? Okay, you can't. EP, if I want to calculate potential energy, that's m times g times h. I need to get joules, which remember are a kilogram meters squared per second squared. Okay, you can cancel mass when you're trying to find a speed or a height, but if you're trying to find one of the forms of energy, mass has to remain in the problem, okay, because it's part of calculating the energy. So keep that in mind for these two. All right, so let's have a look at this one here. So the first thing we want to do is calculate the total initial mechanical energy. Now, why would they say initial if this is a law of conservation of energy question? Do they have to say initial? Or could they just say calculate the mechanical energy relative to the ground at the beginning or at 70 meters or whatever the height is? I mean, they say initial just so we know which ones to use, but initial and final are equal, right? I'm finding the mechanical energy anywhere on this roller coaster when I do part A. All right, so I'm calculating the mechanical energy, which is going to be m times g times h plus 1/2 mv squared. And since this is at the initial point, we'll put in I, but remembering that it's the same anywhere. Okay, so we have a mass of 800 kilograms. And as we said, when I'm calculating an energy, I need to keep the mass, times 9.81 times the initial height, which was 35 meters. Okay, and then I'm going to add to that 1/2 times 800 times 4 meters per second. All right, so we have 281,080 joules. Okay, what would its gravitational potential energy be in the second instance? All right, do they give me a height for the second instance? They don't, but here's the thing. Okay, if I remember this, that my initial mechanical equals my final mechanical, okay, I already know what both of these numbers are. They're 281,080 joules. Okay, as long as I can find some of the stuff about the final part, I'm going to say it's EP final plus EK final. And they told me how fast it's going at the end. They told me it's 20. Okay, so really, if I want to find, my final potential, can I just subtract this over to this side? Would that work? Okay, so I'm going to have 281,080 joules minus 1/2 times 800 times 20 squared. Okay, I'm subtracting that final kinetic energy. That should give me my final potential. All right, so we have 121,080 joules. Now, I probably would have asked that question in this way. How high above the ground is the roller coaster in the second instance? Okay, can I calculate that now that I know the potential energy? Okay, because this number that we just calculated is the potential energy. All I have to do is divide, and I've got the height, right? So I take this number here and divide by 800 times 9.81. Okay, it's still 15 meters off the ground. Okay, is that ringing a bell from last year a little bit? Okay. Anybody need that one anymore? All right, those are really small. Obviously, you can't read them. All right, I want you guys, for right now, just try 1 and 2. So for question number 2, okay, mass of 55 kilograms is 225 meters above the ground, moving at 36 meters per second. So it has both kinetic and potential energy at that point. Okay, using conservation of energy, calculate its velocity when it reaches a height of 115 meters above the ground, ignoring the effects of air resistance. Okay, so we got EI equals EF. Okay, and we've got M times G times H initial plus 1/2 MV initial squared equals 1/2 MV final squared plus MGH final. All right, mass is in every part of this, okay, and we're looking for a velocity, so we don't need it, okay, we can cancel it off and have less to worry about. All right, since I am looking for VF, I need to bring GHF over here, so I'm going to have GHI plus 1/2 VI squared minus GHF equals 1/2 VF squared. Okay, still looking for VF, so I need to divide both sides by 1/2. Okay, and square root. All right, so it's exactly the same calculation we did with the motorcycle question. Okay, when I plug in my numbers, I'm going to have 9.81 times the initial height, which was 225. Okay, plus 1/2 times 36 squared minus 9.81 times 115 divided by 1/2. All right, so should be moving at 58.7, actually 58.8 meters per second at the second point. Yeah. Okay. Now, number 3 is one, of course, you would have never gotten in Science 10, because not only is it a law of conservation of energy question, but it also incorporates projectile motion, which is something we covered in the first unit. Okay, so not something you covered in Science 10. So in number 3, you have a human cannonball who is shot from the cannon at 21 meters per second, 20 degrees above the horizontal, okay, from a platform that's 15 meters above the ground. So they tell us the mass of the acrobat. We're looking for what his gravitational potential energy relative to the ground is when he is at the highest point in his flight. We want to ignore the effects of air resistance there. Okay. And then for part B, the net he lands in is 2 meters above the ground. How fast is he traveling when he hits it? Okay. You don't need projectile motion for part B, but you do need a little bit of projectile motion for part A. So you might need to think back or look back in your notes a little bit, okay, to figure out what you need for part A. Okay, there's something that only projectile motion can give you that we need in order to solve part A. All right, if we are going to calculate the gravitational potential energy at his highest point, what we need to know is how high will he get above his starting point so that we know his height. Okay, and the only way to do that is to use this like a projectile motion problem. So we know he's fired at 21 meters per second. Okay, and we know that that is at a 20-degree angle. So when we were back in the kinematics unit, we were doing these projectile motion problems. We said this side's VI, this side is V horizontal, which I'm not going to need. Okay, but we would do this calculation here, and we would break it up into vertical and horizontal parts. So initially, what I need here, if I want to calculate how high he gets while he's flying here, okay, is I need VI, because I know VF at this point, vertically speaking, is 0. His actual speed isn't 0, okay, because he's going to be moving, but his velocity vertically at that point is 0. So if I can find out what VI is, I can find his height. So I'm going to go sine of 20 times 21, and that'll give me the initial vertical velocity. All right, so the initial vertical velocity is 7.182. All right, now that I have that, meters per second, okay, now I can calculate his height. So VF squared equals VI squared plus 2AD is the formula we always used when we were trying to calculate height. All right, so I'm going to leave height over there. Okay, that'll give me D. Right, we did that a whole bunch of times back in the projectile motion stuff. Okay, so 0 squared minus 7.182 squared, okay, divided by 2 times negative 9.81, and that would give us D. All right, so he's going to end up 2.63 meters above where he started, which was already 15 meters above the ground. Everybody okay with that? All right, so if I add this to 15 meters, there's his maximum height, okay, over the entire flight. Can I calculate his potential energy now that I know his height and his mass? Okay, so it's just going to be times 9.81 times, what was he, 55 kilograms? 56? All right, there's his potential energy, okay, at the highest point. Obviously, he's got more mechanical energy than that because he's also moving, okay, because he was shot out of the cannon. But he's not moving vertically anymore at that point. All right, so should be able to calculate part B. Okay, you didn't even need to do part A to calculate part B. You could have just calculated part B as a law of conservation of energy problem. Okay, tomorrow is Tuesday, right? But because I gave you a short turnaround on your friction lab, you are not going to have a quiz. Get the friction lab done. Okay, make sure that the lab report is finished for tomorrow. Okay. You will have a quiz on Thursday on one work energy, one law of conservation of energy problem.